So we now know how to draw Lewis structures for simple molecules, and we also know that for some molecules, not all, but for some, there are multiple structures that are acceptable. So how do we tell which one of those acceptable structures is the best structure? The way we're going to do that is using formal charges. So here on this slide here, we're starting to talk about how, like I just said, we can draw multiple Lewis structures. The formal charges are going to be our way of figuring out which one is the best structure, and we do that by seeing which structure has the fewest formal charges. Lower formal charges and fewer formal charges overall are better than more. If we have to have formal charges on something, this is something to keep in mind for later. But when we do have to have formal charges on something, it's better to have those on the most electronegative atoms. So we'll keep that in mind for later when we're deciding which one is better when all of the options have the same number of formal charges. Where we put the formal charge will also help us determine which one is better. So all that's kind of jumping in the gun, however, because we don't even know how to calculate the formal charge yet. And that's what it's talking about here. So this is our equation for calculating the formal charge on an atom in a Lewis structure. So the formal charge is the number of valence electrons that that element has minus the number of electrons that are assigned to it. Which then begs the question, which electrons are assigned? And that's what we figure out down here. So the assigned electrons are all of the non-bonding electrons, which is to say the lone pairs, plus half of the bonding electrons. Another way of saying that would be 1 for each bond. So if you have just a single bond, you would get 1 electron from that. If you have a double bond, you would get 2 from that. You get 1 electron assigned to an element for every bond that it participates in. And if it has a lone pair, then it gets assigned both of those, which should make sense because those aren't connected to anything else. They are on that atom and that atom only, and so that atom is assigned those electrons. So the formal charge is the valence electrons minus the assigned electrons. So if we look at a few examples here, we have 2 different structures that you could make with the elements hydrogen, carbon, and nitrogen. So we could either have the carbon bonded to the hydrogen, or we could have the nitrogen bonded to the hydrogen. Either one of those can give you a structure that is acceptable based on our Lewis structure rules. Both of these here are acceptable. Everything that wants an octet has one. But one of these structures is better than the other, and we can see that when we look at the formal charges. So when it's arranged as HCN, where the hydrogen is bonded to the carbon, hydrogen, as long as it has just the single bond, it's always going to have a formal charge of 0 because it has 1 valence electron and it only has 1 bond, and so if it gets 1 of those electrons assigned to it, that would be 1 minus 1, which gives you 0. And it's going to be the same thing for the hydrogen over here. Carbon here has 4, well, carbon always has 4 valence electrons. In this particular structure, it has no lone pairs, and so it has 0 non-bonding electrons, but it has 4 bonds. There's 8 electrons participating in those bonds, so it gets half of those, which again is just to say it gets 1 for each bond. So 1/2 times 8 gives us 4, so 4 minus 4 gives us 0. So the carbon also has a 0 formal charge here. And the nitrogen in this structure also has 0 as its formal charge. It has 5 valence electrons. Nitrogen always does. In this particular structure, it has 1 lone pair. Both of those electrons get assigned to the nitrogen. So it has minus 2 from the non-bonding electrons from the lone pairs. And because because it's participating in 3 different bonds, it gets 1 from each of those, or 6 times the half, which would be 3. And so minus 2 minus 3, it also is 0. So this structure is looking pretty good. If we look at the other one, we already looked at the hydrogen. We're just going to concern ourselves with the nitrogen and the carbon here. In this particular structure, the nitrogen no longer has a lone pair. It still has its octet, so it's still fine from that perspective. But because it does not have a lone pair, and because it has to share all of its electrons, it no longer has the -2 here like it did over here. Now it's just 0, and it's going to be 5 minus 4, because it's participating in 4 bonds, and so it's going to have a formal charge of +1. Similarly, the carbon, which did not have a lone pair before, now does. It's essentially swapped places. Well, not essentially, it literally has swapped places with the nitrogen from over here. So it now has the -2 and then the -3 from the bonding, and so it, because it only has 4 valence electrons, it actually has a negative formal charge. So in this structure, we had no formal charges. In this one, we have 2. One with +1, one with -1. So is this an acceptable Lewis structure? Yeah. Everything is following the rules. Everything has an octet that wants an octet. Is this the best Lewis structure? Absolutely not. This is actually quite unstable. You could have a molecule like this, and I'm sure someone in a lab somewhere at some point has made this. It can exist, but it is not very stable. It would much rather be in this configuration. And I would bet you that if you make this molecule, it will pretty rapidly do what's called a reconfiguration, and this bond will flip, and you will get it turning into this, just because this is much more stable here. So while this is acceptable, it could work. You could have a molecule like this. It is not the best structure. This one is better. Okay, another example here. In this case, we actually don't have a rearrangement of the atoms. This is a more commonly seen example here, where we're not moving the atoms around, we're just changing how it's bonded. We're not actually changing what is bonded to what. We are just changing how they are bonded in terms of where the electrons are. So we have 3 different ways of arranging the electrons here, and again, all 3 of these give you acceptable Lewis structures. Everything in all 3 of these examples have a full octet. If we look at carbon, for example here, and we're just going to look at all the carbons at once because they're all the same in the grand scheme of things. The carbon here, which has 4 valence electrons, has no lone pairs in any of the situations here. And in all of them, even though in one situation it's 2 double bonds and in the other 2 it's a triple and a single, still it ends up just being 4 bonds total. So you get 1 from each of those bonds. And so all of the carbons end up being 0. So the carbon's not really going to help us determine which of these structures is better. It's going to be the oxygen and the nitrogen. So if we look at the differences here, excuse me, oxygen in this structure has 3 lone pairs and a single bond. So we're going to take its valence electrons, which has 6. It's going to have -6 from the lone pairs, and then 1 from that bond, which is going to give it overall -1. The nitrogen, on the other hand here, has 4 valence electrons. It always does. Nitrogen is always 5. I think I said 4. It has 5 valence electrons. It always has 5. It has a single lone pair. So we have -2, because both of the electrons in the lone pair are assigned to the nitrogen. And then it has 3 bonds. And so it gets 3 assigned to it from those bonds. And so overall, it is 0. So this molecule is not looking too bad, but let's look at the other ones. So here, the oxygen has 2 lone pairs and 2 bonds. So it gets all 4 of the electrons from the lone pairs, and then 1 from each of the bonds, and so now this oxygen is 0. So that's looking pretty good too. The nitrogen, on the other hand, now has an extra lone pair compared to what it was over here. Essentially what we did going from here to here is we pushed the electrons like this. So we made a double bond and then pushed that pair up to a lone pair here. And so we get to this structure, which looks pretty nice. It looks nice and symmetric. The nitrogen, though, with 5 valence electrons, 4 assigned to it in the 2 lone pairs, and then 2 bonds, gives it a -1. So overall, in terms of the formal charges, it is the same as example A here, or structure A. Structure C, on the other hand, it's rough. So if we look at the oxygen here, it has only 1 lone pair and 3 bonds. So it gets -2 from that lone pair, -3 from the bonds, which gives it +1, which is really not what oxygen likes. Oxygen is quite electronegative, and so it is not going to like having so few electrons assigned to it. Nitrogen, on the other hand, with 5 valence electrons, has 6 in lone pairs. So that already, just on that, would put it into the negative in terms of formal charges, but then it gets another one assigned to it from the bond. And so it has a formal charge of -2. So this is by far the worst. Not only does it have more formal charges, not only does it have formal charges on more atoms, but even the formal charges on those atoms are larger than the other two. So this is definitely the worst one. So then the question becomes, which one of these two is better? Because they have the same overall formal charges. It's just we have to pick, do we put that formal charge on the oxygen, or do we put the formal charge on the nitrogen? Does anyone remember how we decide? We discussed it just a minute ago, actually, on the previous slide. If we have to pick where to put a formal charge, the more electronegative atom is better at holding that negative charge. And so in this case, A is the best option. Oxygen is more electronegative than nitrogen, I believe 0.5 more, if I remember correctly. And so this is the best structure. Now, does that mean that B is a bad structure? No, it's not bad. It's just not as good as A. It is a matter of gradations. Either one of those are acceptable structures. Technically speaking, even this one is an acceptable structure, even though it is by far the worst structure. But these two are much closer to each other than this one would be. But A is the best structure. All right, so a little bit more here in terms of examples with formal charges. We're going to draw 2 structures of carbon dioxide. We saw one of them in the last video, and that was this. So this was the structure we built in the last video. The other structure you might have gotten is this. And by the way, you could just flip that and have the triple bond on the other side. It doesn't really matter. But this is also an acceptable Lewis structure. The oxygen, carbon, and other oxygen here all have an octet, but one of these two is better than the other. If we check the formal charges here, carbon has 4 valence electrons. It has no lone pair electrons, but it does have 4 bonds, and so it gets 1 from each of those. And so the carbon here is 0 in terms of its formal charge. And same thing for this one. It's going to be 0. This oxygen is going to actually have the same formal charge as this oxygen because they're bonded exactly the same. They both have 2 lone pairs and 2 bonds. So the oxygen has 6 valence electrons. It has 4 electrons in lone pairs, and 2 from the bonds are going to be assigned to it. So it has 4 electrons overall in the bonds. It gets half of those, and so it gets 2. And so this is also 0. So all 3 of these atoms have 0 formal charge. I'm betting that's going to be the most stable one, the best one. But we can check this just to be sure. These 2 oxygens are going to be different. They're going to have different formal charges because they are not bonded the same way. So this oxygen still has 6 valence electrons, just like any other oxygen, but it only has 2 electrons in lone pairs, and it gets 3 assigned to it from the bonds, and so it is going to be +1, whereas this oxygen has 6 in lone pairs and just a single bond, and so it is going to be -1. So we have a +1 and a -1. And so this structure is the best structure. This is the better structure, where it's more symmetric. Although, as we'll see in just a second, just because it's more symmetric does not necessarily mean that it is the better structure. Just in this case, it happens to be the case. Alright, let's do the same thing real quick. This will be the last thing we do for this video. Let's do the same thing with NCS-, thiocyanate. So we are going to have 3 different options for thiocyanate. And I would like you, starting from this point, to pause the video and try to work out what the 3 possible Lewis structures are. So go ahead and pause the video and see if you can work out what 3 different structures are, not moving the atoms around, just 3 different ways for them to be bonded together. Alright, first thing we're going to do here. Let's work out how many electrons we have to put in. So we're going to get 5 from the nitrogen, 4 from the carbon, 6 from the sulfur, and then 1 extra from the negative charge. So that's going to give us 16 electrons total. We have 2, 4 in the bonds already. So starting from there, I believe the nitrogen is more electronegative, and so I'm going to start putting them on there first. So 4, 6, 8, 10, 12, 14, 16. So this is going to be our starting point here. Obviously the carbon is not happy, and there's a few different ways we can fix that. So we could make a triple bond over here, for example. So let's go ahead and do that. If we make a triple bond here, we would be moving these 2 lone pairs in to make that bond, and if we do that, everything that wants an octet has one. Alternatively, if we start at the same point as before, where the nitrogen and the sulfur are full up with their octet, but the carbon is not, we could have moved in a single lone pair from both sides and gotten this, or instead of moving in to make a triple bond to the nitrogen, we could have made a triple bond to the sulfur instead and gotten this. So those are our 3 options. If we try to figure out which one of those is better, once again, we're just going to be using the formal charges to work that out. Carbon is going to be 0 for all of these. I'm not even going to bother calculating that. It's just carbon with 4 bonds. It's always going to be 0. So we're going to have nitrogen, which has 5 valence electrons here on the left, and we're going to have sulfur with its 6 valence electrons on the right. So in this structure, nitrogen has 1 lone pair. It gets both of those electrons. 3 bonds. Gets 1 from each, which gives us 0. Nitrogen here 2 lone pairs, 4 electrons, 2 bonds, 1 from each, so 2. 5 minus 6 gives us -1. In this structure, nitrogen has 6 valence electron, or sorry, 6 electrons in lone pairs. It gets all of those assigned to it, plus another one from the bond, giving us -2. Okay? I'm already getting the sense that this might not be the best option, this structure. So if we take a look at the sulfur, in this structure, sulfur has 3 lone pairs, so it gets all the electrons from those, and 1 bond. That gives it -1 as its formal charge. Sulfur here, only 2 lone pairs, so 4 electrons, and then 2 from the bonds, which would be 0. And then the last one here, only a single lone pair, so it gets both of those. 3 from the bonds gives us +1. So 6 minus 5 gives us +1. So this structure, the one on the bottom here, obviously the worst. We have -2 and +1 for our formal charges. So we're once again met with the decision of which one of these two is going to be better, because it's just a choice of, do we put the -1 on the sulfur, or do we put the -1 on the nitrogen? And you can double check me to be sure, but I believe the nitrogen is more electronegative. I think nitrogen is 3 and sulfur is 2.5. But that is purely going off my memory, so I could be misremembering that. So check me, just to make sure that I'm right. But if I am remembering correctly, this would be the best structure. That would not necessarily mean that this is a bad structure, but it is not the best structure. So, all right. So, that begs the question. I know it's kind of covering up the text there, but if there are 3 possible structures, we've already determined which one is the best structure, but which one is the correct structure? We'll talk about that next time.